The lift hill on a roller coaster uses a chain lift. And how many of you have ridden a roller coaster? A simple chain lift roller coaster. So the roller coaster gets you up and crests the top of the first hill. Now there may be ride elements thereafter. You may have, like the Scorpion has an initial first loop, then it goes off and does other things. The chain lift is probably the cheapest way to do this, to add energy to the ride. The chain lift does work on the cars. It's an external agent that is applying a force this direction on the cars. That whole time, the cars are also experiencing another force, gravity, and a normal force. Now, which of these forces are doing work on the cars? You should be able, based on our definition, to tell me which of these three forces do work on the cars. If you can't, or you don't have a reason, or don't understand why I'm asking this question, then you're not writing enough in your notes. So I'll remind you, the only forces that can do work are forces that have components in the direction of motion. Does this force have a component in the direction of motion? So it's doing work. Does this force have components in the direction of motion? Yes, it does. It's against the direction of motion, but still in the direction of motion. So it's doing negative work. Remember, you're lifting something up, you do negative work against gravity. Is a normal force doing work? No. It doesn't have any component in a direction of motion. So of these forces, two of them do work. The external agent here is the chain lift. It's doing work on the roller coaster cars, and it's giving them gravitational potential energy like we talked about yesterday. Once the cars reach this point, the chain lift disengages. And the only active forces at this point are what?
Gravity and normal force.
So gravity and normal force. And again, is the normal force doing any work on the cars? Does it have any component direction of motion? It doesn't even matter really where it is, right? If I'm over here, and the cars are going this direction, the normal force is this way. It's still not doing work on it. So the normal force never does work on the cars. But the gravitational force is always doing work on the cars. In this case, the gravitational force is doing positive work, speeding the cars up. Would you guys agree with that statement? In fact, we would be able to say that net work is being done by gravity on the way down. Because there's only one force doing work, it's an unbalanced force, and therefore it is changing the kinetic energy of the cars. You guys follow that so far? Now, if you remember yesterday, I said that we define gravitational potential energy as minus the work done by a conservative force. As the car travels down the ramp, is its gravitational potential energy increasing, decreasing, or staying the same? I'll remind you, this is how we calculate gravitational potential energy. So would you guys agree that the height's getting smaller? So it has less and less gravitational potential energy. Its potential energy is changing. Delta means change, correct? And this is because net work is being done on the cars to change its kinetic energy. Now, this part might be difficult for you guys, but I'm going to try and do it anyways. If we put these two things together, then by simple substitution, the change in potential energy is going to have to equal minus the change in kinetic energy. As the car's potential energy decreases, the car's kinetic energy increases. Does that make sense? And we're seeing that this direct relationship must be here, assuming that we're dealing with work being done by a conservative force. Now, this next part is a little heavy in the algebra, so I hope that you can follow along. What does delta mean? So final minus initial. So U final minus U initial. That has to be the same thing for delta K. Has to be K final minus K initial. All good? I want to distribute that negative sign. So when I distribute that negative sign, that makes K final negative, but makes K initial positive. Is that all good? All right. Now, what I would like to do is I would like to collect all the things that say final and put them on the same side, and all the things that say initial and put them on the same side. You guys okay with that? So I'm going to move this one over here. I'm going to move this one over there. And I'll get potential energy final plus kinetic energy final equals potential energy initial plus kinetic energy initial. Now, I don't know if you kind of grip what's happening here, but this statement says that if I add up all of the energy I have at one point, it has to equal all the energy I have at another point. This is a conservation rule, and it's the first conservation rule we're going to have, conservation of energy. Now, we're talking about physical energy right now, but conservation of energy is a very big topic in science in general, and a very easy to recognize topic in physics in particular. What this tells us is that if there's no external force on the system, the amount of energy in the system remains unchanged. It can change form. It can go from one form of energy to another form of energy, but the total amount of energy in the system remains unchanged. Now, you may not understand what that means for us right now, but I want to give you an example of how we're going to use this, like what its meaning is. First, I said to you yesterday that the change in potential energy only works if we're dealing with a conservative force. This statement of conservation of energy is predicated on the idea that the only forces doing work are conservative forces. If you don't know what that statement means, it means that if there are other forces doing work that aren't conservative, then energy won't be conserved. Energy is only conserved if conservative forces are acting in the system. If there's other forces acting, then you have to find different ways to track that energy. For example, if friction were acting in this ride, friction would be taking energy out of the system in a way that we can't get that energy back. Because of that, friction would take the energy out permanently. It wouldn't just get reciprocated back into the system. Then we'd have to account for that. Air resistance would do the same. Sound would do the same. All of these are ways in which energy will leave the system in a manner that can't be recovered. A conservative force is one in which the energy can be recovered. I throw a ball into the air, turns into gravitational potential energy, comes back down, turns back into kinetic energy. The energy is being recovered. There are a couple of conservative forces in which this occurs. And there's several different forms of energy that use those conservative relationships. Chemical potential energy does it. Electrical potential energy does it. These are all different ways to store energy. We're going to look at just physical ways, and the only one we have right now is gravitational potential energy. So consider the chain lift. The chain lift lifts the cars to here. The top of most roller coasters, you're barely moving. That's on purpose. They want the amount of kinetic energy there to be very little. That way you're up there for a long time, and you might have a little bit of, I'm scared because I'm up high and I don't know what this ride's going to be like. Probably any little kid who's ridden one of these for the first time is a little scared. And they don't make it any easier on you. That noise you hear the whole time you're going up, that clackety noise, that is terrifying to a child. It should be reassuring to all of you. You guys know what that noise is, right?
Yeah.
What is it?
It's keeping the cart on the track. Just kidding.
Oh, no, I hope not. But it is keeping something together. But it's not keeping the cart on the track. The cart's on the track because of the three-wheel system. That's what's keeping it from doing. It's a lever. And if you'll look on the track, you'll see this little stair-step pattern. It's smaller than what I'm drawing here, but it's really small like that. It's all the way up the track. All of the cars have this little lever that's bouncing in that. That's that tick, 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 tick you hear. That's that thing. If the chain were to break, and they do, or the motor were to be stripped, and it happens, the cars would roll back into the loading house. That's incredibly dangerous and has hurt people in the past. Hulk does it every once in a while. So what they have in place is this system that locks the cars back in place if they try to roll backwards. It's there on purpose. That's why all the roller coasters, you hear that noise. That clickety noise are those ratchets bouncing into those gears the whole time. There is a ride that doesn't do that, and it's purposeful. They don't want you to hear it because it blows the illusion of the ride. Has anybody ridden Everest? Everest purposely lifts that bar up using magnets so that it won't make the clicky noise, but it's still there. The moment the wheels stop moving, the magnets disengage and it falls into place. But they wanted to lift it up to make it appear as though you're on a train. That was the whole point. In fact, when you go to the loading dock, the reason smoke comes out is because there's a smoke emitter in the base of the tracks that pushes smoke through the front of the train to make it look like it's coming out of the chimney of the train. Never actually does. It's just still a dumb roller coaster, meaning it's not smart, doesn't have any added features. It's just gravity fed the whole way. Now, this is not true of the rides that use a launch system. Some rides do direct work on the cars using a launch system. They add energy to the system using some kind of either electromagnetics or some kind of hydraulics. So you guys, anybody ride Cheetah Hunt? So Cheetah Hunt is electromagnetic induction motors. We build them in E&M. They're pretty simple, and they just shoot the cars forward. Anybody ride, say, a Hulk or Rock and Roller Coaster? That one does not use electromagnetic induction. It uses a hydraulic system the same way they would launch planes off an aircraft carrier. It's very reliable, except in Hulk's case, because of the way Hulk was designed. It used to have an incredible fail rate. They call it Wing when a roller coaster rolls back into its main house. Hulk often failed to launch in its early days of release. It has since been updated, and now it has a much better reliability rating. You know what they don't use to launch cars? They don't use springs. Although incredibly reliable, they tend to kill passengers. So we don't use spring systems to launch roller coaster cars. It's because of the way they apply their forces. Springs apply their force the greatest at the very beginning. That causes almost all the riders to have whiplash. So they want to have a little bit of ramp up to the main acceleration, just enough to get your head set in place. That's why if you've ridden Hulk or you've ridden Rock and Roller Coaster or even Cheetah Hunt, you have a second to get your head kind of in place before you get launched. And Cheetah Hunt doesn't launch you particularly fast, but Rock and Roller Coaster and Hulk do. And they can be dangerous if you don't have your head in place initially. Well, you're not going to die, but you're probably going to learn a hard lesson if you have your head away from that pad in the back. Anybody ever accidentally done that? And it slams your head back? Not entertaining. All right, back to work here. So let's go back to this idea that we are on the track. I want you to consider the four places that are indicated: point A, point B, and point C. And let's say, for argument's sake, that this is not the Scorpion, but some generic roller coaster that has a 360 loop with a radius of 10 meters. And let's say the lift hill is, we'll go with 30 meters tall. All right? At the very top, what kind of energy do the cars have? Gravitational potential. If the cars are moving very slowly, we can assume they don't have hardly any kinetic. This is the first point in our ride and represents a point where we know the energy of the system. Now, as the car rolls down to point A, what kind of energy do you think we have at point A? Do we have any gravitational potential?
Yes.
Are we above the lowest point in the ride?
No.
We're not above the lowest point here?
Oh,
I think we're above the lowest point. No. The lowest point of the ride would be here, but I think we're above the lowest point in the ride there. Wouldn't you agree? Are we as high as we started? No. So we probably have less potential energy than we had. Where do you think that energy went to? Kinetic. The cars are moving, likely has kinetic. What conservation of energy says is this amount of energy has to be equal to this amount of energy. If only a conservative force is doing work on the cars, the amount of energy at one place has to be equal to the amount of energy at another. That's what this statement says. In fact, down here, what kind of energy do we have here?
All kinetic.
Is there any reason to say we have potential? Are we above the reference level? Are we above the lowest point in the ride? No, if we're at the lowest point, there's no potential, but we probably have lots of kinetic. That's probably where we're traveling fastest. In fact, do me a favor. If we're at the 25 meter mark, and this we're at the ground, can you figure out how fast we're going at each location? You have calculators there. I'll help you with the first one, and then you do the second one, okay? Let's compare the starting state here with state A here. Starting state, I have all gravitational potential. Do you recall gravitational potential? mg h minus h naught. This just represents the change in height from the lowest position. Kinetic energy, 1/2 mv squared. So at the very top, I have mg h. No kinetic energy, so all of my energy is in the form of gravitational potential. Don't know the mass of the cars. Not sure I'm going to need it. At state A, I have gravitational potential because I'm above the lowest point, and I am 25 meters above the ground. But that's less potential energy than I had. That remaining energy had to go somewhere, 1/2 mv squared. Using gravitational potential energy, I don't need to know the angle of the track. I don't need to know if it's straight or curved or anything like that, or even the length of the track. All I need to know is the comparison of the two states. Gravitational potential energy is what we call path independent. Doesn't matter what path you take to get to that height. All that matters is what that height is. And conservation of energy states that the energy at one state has to be equal to the energy at another state. So all I have to do is set those two states equal to each other. One of the first things you'll notice is that I don't need the mass of the roller coaster cars. There's mass in every term. You've never been asked what your mass is when you got on a roller coaster. This is why. Now from here, you should be able to figure out how fast we're going. I'm noticing I got 300 on this side, 250 on this side, plus 1/2 v squared. Do a little math, and I'm thinking 300 minus 250 is 50, times 2 is 100, so v has to be plus or minus 10 meters per second. You guys can do the arithmetic on your own if you don't believe me. Conservation of energy is really good at telling you height, velocity, or displacement. It's very good at those things. And it's very fast. You notice we never had to find out what the force was. We never had to find out what the acceleration was. I didn't need how long it was moving. All I have to do is compare any two states in the problem. Tell you what, you guys try another one. You guys find out how fast we're going at B. Do the work. I want to see you try it. If you set those two equal to each other, you found mg times 30. And there's no potential energy here, so that just ends up being 1/2 mv squared. I don't have to set this one equal to this one. I can set any two states that I want together. So I set this one equal to this one because this is easier to work with. Again, the m's cancel out, and you get v equals the root of 600, which is what, like 25? Again, plus or minus. The thing that you have to understand about this is it can't tell you what direction you're going. You have to get direction from context. Like, I knew that here I had to be going down the track. Here I have to be going this way. But you can't get directional information from energy. Energy is a scalar. So you can only get directional information through context. By knowing where it is on the track would be one way. Now, there's really not much else about this, but I do want to talk about why I've written it this way. why I put h minus h naught here. The first thing I want you to understand is that this is path independent. I've said that a couple of times, but I want to say it again, and I want to elucidate what I mean. If I take a box and I put it up here, and I ask how much potential energy it has, it doesn't matter if I walked the box up the ramp this way or I lifted the box to here. I can show you that it doesn't matter, but I want you to understand that that's really mathy. And I want you to understand that all that matters is the absolute change in height. That's all that matters. So no matter which path I take to get to this height, once there, the amount of potential energy is based on that change of height. That's it. And that means this is the change of height. That's what I mean when I say that gravitational potential energy is path independent. That it's just based on the absolute change in height. Now, that being said, there is a difference between going this path back down and this path back down. And when I say there's a difference, well, there's the potential to have friction on this path back down. Friction would do work on the system and would take energy and transform it into something else. So you do have to be careful about whether there is or is not other forces acting in your system. Non-conservative forces transform the energy into unusable values, into things where you can't get the energy back. Friction creates heat. Air resistance creates heat and sound. These are forms of energy that you can't easily recover. They can't be contributing to the kinetic energy. They take energy away. Also, I want to take issue with H naught. H naught represents what we call the reference level. Where are you measuring the height from? Now, we say that anything that has been lifted to a certain height has gravitational potential energy. In fact, what I said to you is that it's energy that's related to the object in the earth. We would say that there's a relationship there, and that the earth, whatever, object system has gravitational potential energy. But you have to understand there's a certain function in this. Does my coffee cup have gravitational potential energy?
Yes.
See, we say it does because it's higher than what?
The floor.
Which floor?
This floor.
Are you sure? I mean, I had to bring it up here from the first floor at some time. On the other hand, it's never going to fall off my desk. I mean, unless I perch it precariously over here. Now, there's the potential it could fall off my desk. What I mean is, all of these things are created to help us understand and perhaps solve problems. If my cup is never going to fall off my desk, does it matter if it's above the floor? When we talk about potential energy, it's about its useful function, its useful service. So, I mean, we could say all the stuff in this room has potential energy because it was all lifted up off the floor from downstairs. But when we talk about it, I mean, work was done. I had to lift it up to get it up here, and then lift it to put it on my desk. But having potential energy is more about what the object can do, and not about what the object has had happen to it. Do you follow my difference? I don't think the cup's going to fall off my desk. Do I care if it has potential energy? No. It has no potential energy relative to my desk. Now, when you guys knock crap off my desk, well, those objects had potential energy relative to where they could fall to. So when we talk about potential energy, we talk about it in a relative manner. And that's why I want you to have that H naught. Imagine this. What if I have a skate park where there's a 3-meter rise and then on the other side a 1-meter rise? And you are here on your skateboard and you're moving at 2 meters per second. And I want to know, if you don't kick on your way around, how fast are you going here? What kind of energy do you have here?
Kinetic and potential.
Sure, I have gravitational potential and I have kinetic. And what kind of energy do you have here?
Gravitational and kinetic.
You could say gravitational, and you're likely going to have kinetic too. But hear me out. Why couldn't I just set the reference level to be here? This is going to be the lowest point between here and here. Yes, I will make it to a lower point somewhere in the ride or somewhere on the trip. But if I never ask about being here, I can set my relative height to be here. It won't make any difference in our answer. In fact, let's say that we set the height down here. Okay? We'll have mgh plus 1/2 mv squared for the energy here. Correct? You guys see what I've done? Any question about those choices?
Wouldn't it be 2 meters if we're in the base?
I'm saying we're going to use this as our reference, all the way down there. This side we're going to have mg times 1 plus 1/2 mv squared. But if you're seeing what I'm about to say, if you subtract this from both sides, you just get mg times 2 plus 1/2 m times 2 squared equals 1/2 mv squared. You understand, resetting the reference level doesn't change your problem at all. It's just reference. Your height is reference. What you should put in your notes is that to use conservation of energy, you have to use the same reference between any 2 points. Height has to be measured with the same reference between any 2 points. You can't change reference when comparing 2 points. That's why we write it as mg h minus h naught, for you to ask yourself, where or what should I use as my reference height? Ask the question and then proceed from there. I suspect these are just plug and chug right now. And I'll just sum up. We have 2 forms of energy. Potential and kinetic. No external force is doing work on your system. The amount of energy in the system remains unchanged. However, I'm going to add a form of energy. Springs are another conservative force. They can store energy. When you take a spring and compress it, you do work on the spring. So consider I have a box here. If I push it against the spring is a restoring force. It wants to stay its original shape. So if I push the box against the spring gets compressed. Now, you guys are pretty shrewd and played with toys before. If I let the box go, what does the spring do?
Push the box.
It's going to push the box back. It just so happens that the spring acts as a conservative force. So there's energy stored in the spring mass system. Now, this only works, of course, if there's a fastening point that holds the spring in place. I think that's obvious. If there wasn't one of those there, the spring wouldn't compress. So there has to be something that holds one end of the spring in check and allows you to compress the spring. But if I do, energy will be stored in the spring mass system. I'm saying it very carefully because remember, the box doesn't have energy. The box and spring together have energy. This is another form of potential energy and is based on how far you compress the spring, and it's based on something called the spring constant. We use a lowercase k as the spring constant. Sometimes called the Hooke's law constant. This is known as elastic potential energy. And although I'm saying it about a spring, rubber bands have elastic potential energy, the bow from a bow and arrow would have elastic potential energy. Anything that you deform that springs back into its original shape is elastic potential energy. Even an inflated ball has elastic potential energy. That's why they bounce. So they can store energy, and when released, that energy can transform the kinetic energy of an object. Even like a rubber band, you can store the energy in the rubber band, and releasing it puts the energy into the rubber band in the form of kinetic. Anybody ever flick a rubber band at somebody? That's just a simple conservation of energy relationship. The amount of energy stored in a spring or a piece of elastic is 1/2 kx squared. I can't prove that to you because it requires calculus, or it requires a lot of discussion about graphs, neither of which I want to do. But it's just another form of energy and behaves the same way. So conservation of energy now involves 3 possible places where energy could be. So ask yourself, am I above the reference level? If you are, you have gravitational potential energy. Are you moving? If you are, you have kinetic energy. Are you pushed up against a spring? If you are, you have elastic potential energy. It's easy to spot. You won't have elastic potential energy unless there's a spring involved. And if your track is completely level, there'll be no chance for gravitational potential energy. But I think it's pretty easy to spot when you'd have one versus the other. And all you have to do is add up the energy at one place and set it equal to the energy at another place.